In this video, we're going to cover electric fields. The electric field starts with Coulomb's law. F is equal to kq1 q2 over r squared. This gives the force between two charges, q1 and q2. Similarly to the gravitational force, no contact is needed between the two charges for them to feel a force from the other charge. We call this a field force, or forces acting at a distance. This action at a distance is best understood by assuming that each charge has a field surrounding it that affects other charges. This is called the electric field. When we were talking about Newton's law of gravitation, we called it the gravitational field. Let's find the electric field due to one charge. The notation in Coulomb's law will be modified slightly, assuming that one charge is very large and the other charge is a small positive test charge that will have a negligible electric field due to its size. The large charge will be labeled capital Q and the small charge lowercase q. The distance between them will be labeled r. The absolute value signs will be removed as we will now consider the vector quality of the force. Note the arrow on the top of the force, that means vector. It has magnitude and direction. Of course, they're not giving you the direction here, so we will go ahead and put one in as r hat. To find the force that the large charge exerts on the little charge, the above equation will be divided by q, the lowercase q, and this will be defined as the electric field. The electric field now shows both magnitude and direction of the force exerted by q on any charge. To find the force, the electric field is multiplied by the charge that is being considered. So now let's go through this a little bit so that you understand what this means. We're really looking for the electric field of the large Q. So we take this equation here, kq times divided by r squared, and that gives us the electric field of this charge. In order to find this charge, this electric field experimentally, we would have to bring in a little tiny charge called q. Now, if we take the force that's exerted on this object, this little q, by this big Q, and divide it by the amount of that charge, that would give us the electric field strength. So this is this little q, this is this big Q. Okay, so when we're solving for the electric field, we're looking for the electric field of the big charge Q. The charge capital Q creates the electric field. The size of charge Q and the distance to a point determines the strength of the electric field at that point. The electric field strength is measured in newtons per coulomb. The electric field is represented as a group of lines that shows its direction but also its strength. The electric field lines are used to compute the magnitude and direction of the force on any charge placed within that field. When you multiply the strength of the electric field at any point by the charge which is placed there, it gives you the magnitude of the force on that charge. The direction of the field gives you the direction of the force on a positive charge. So the force on a negative charge would have to be directed in the opposite direction for a negative charge. The electric field lines, which are imaginary, help us to visualize what's going on. They originate on positive charges and they end on negative charges. If there is an isolated positive charge, it will create an electric field that points radially away from it in all directions, since a positive test charge in the field will be repelled by this charge. Okay, so for a positive charge, the electric field lines radiate outward. The charge creates a spherical symmetric field since it is proportional to 1 over r squared. At any distance r from the charge, the value of the field must be the same. Since R can point in any direction, we get the field lines centered on the charge, generating a sphere. Remember, a charge exists in 3 dimensions of space, which is represented in 2 dimensions here in this picture. And imagine that all of these lines come out in all different directions, radially outward. If there is an isolated negative charge, it will create an electric field that points radially towards it in all directions, since a positive charge in the field will be attracted to this charge. So here we have a negative charge, here we have a positive charge. The positive charge will be attracted to the negative charge, and therefore that is the direction of the electric field. The definition of the electric field shows that the strength of the field decreases as distance increases. In other words, it's an inverse square law. This can be seen by looking at the density of the field lines. Notice that here, as you're closer to the object, they're more dense, and therefore it's going to be a larger field strength. As you move away, notice they're separated more and more, and that gives you a lower electric field strength. If you want, you can go ahead and look at the simulator from PhET. I'll make that available on Edmodo. The electric field is attributed to Michael Faraday. Faraday was born in London in 1791. He came from a poor family. At 13, he apprenticed as a bookseller and binder, while also attending local lectures on philosophical and scientific topics. A member of the Royal Institute took notice of Faraday and bought him tickets to several Royal Institute lectures. In 1813, he was invited to work at the Royal Institute, where he made numerous contributions to physics and also chemistry. So let's go ahead and do an example. Find the magnitude of the electric field for a charge of 5.6 nanocoulombs at a distance of 3.0 meters. Okay, go ahead and pause the video, but before you do that, make sure you convert nanocoulombs to coulombs. Go ahead and pause now. Okay, so let's go ahead and see if you have the correct answer. The electric field is equal to kq over r squared. Substituting in the numbers, the magnitude of the electric field should be 5.6 newtons per coulomb. A 4.5 millicoulomb charge experiences an electrical force of 9.0 millinewtons in the presence of an electric field. What is the magnitude of the electric field? Go ahead and pause the video now. Okay, so let's take a look at your answer. Hopefully you remembered that you had to convert millicoulombs to coulombs and millinewtons to newtons. The force is equal to QE. E is equal to F over Q. Taking the force and dividing by the charge ends up giving you 2.0 newtons per coulomb. If E naught is the electric field generated at a distance r from a charge Q, what is the electric field at a distance 2r? Go ahead and pause the video now to see if you can come up with the answer. Okay, so let's check and see what you have. Hopefully you substituted in 2r into the denominator and squared both terms, which ends up giving you an electric field at a distance of 2r, which is actually 1/4 the original field at distance r. The direction of the electric field can be found by using A, the direction of the gravitational force, B, the direction that a positive test charge would accelerate, C, the direction that a negative test charge would accelerate. Go ahead and pause the video if you need to and select the answer. Okay, so let's see if you chose the correct answer. Hopefully you chose B. The direction of the field is in the direction of the positive test charge would accelerate. What is the direction of the electric field at points 1, 2, 3, and 4? Is it up, right, down, left? Is it up, left, down, right? Is it down, right, up, left? Or is it down, left, up, and right? Go ahead and pause the video if you need to. Okay, so let's go ahead and see if you've chosen the correct answer. The correct answer is A. It's up, down, left, up, right, down, left. What is the direction of the electric field at points 1, 2, 3, and 4? Is it A, up, right, down, left, B, up, left, down, right? Is it C, down, right, up, left, or is it D, down, left, up, right? Okay, so let's see if you have the correct answer. Hopefully you chose D. Remember, the electric field points towards the negative charge instead of radially outward. In the next video, we'll talk about electric and gravitational fields.